Hey guys, welcome to video 72. Today we're going to complete our analysis of the Marshall SLP preamp. We previously analyzed input sections 1 and 2, and here are the resulting values we got for those two analyses. And we're going to finish up today by looking at stage 3. And if I sound a little different, it's because I'm recovering from being sick all last week. And it feels good to get back into things, so let's go on over and take a look at stage 3. Okay, here's our circuit and the plate curves for the 12AX7. We actually have two stages here. The first stage is an unbypassed common cathode amplifier driving a cathode follower. So V2A is going to have a substantial amount of voltage gain. V2B will have a voltage gain of approximately 1. And because these two triodes are directly coupled, it's going to complicate the analysis just a little bit, but nothing too crazy. So let's start with the analysis of V2A. Remember, under normal operating conditions, V2B represents an infinite resistance connected to the plate of V2A, so we can disregard the loading effects of V2B. All right, let's start by finding VPK cutoff for V2A, and that's going to be VPP, which is 260 volts. IP saturation for V2A is approximately VPP over RP. We can disregard RK because it's so small compared to RP. And that's 260 volts divided by 100 k ohms, which is 2.6 milliamps. Okay, so let's draw our DC load line in here. 2.6 mils is right here. 260 volts is here, and there is our DC load line. Next, we construct our bias line, so we're going to choose convenient values of VGK and determine the resulting plate current. And remember, I sub P equals VGK over RK, and the easiest place to start is with VGK of 0, which produces a plate current of 0. So here's our first point, and let's use the VGK equals negative 2 volt curve. That's right over here. So using negative 2 volts, that gives us a plate current of 2 volts divided by 1K, or 2 milliamps. So our second coordinate here is 2 milliamps on the negative 2 volt curve. That's right here. Let's switch our color to green as usual, and we'll sketch our bias line. And here it is. Now switching over to purple for a little bit of contrast. Here's our Q point. And coming down from there, it looks like we've got a VPKQ of about 155 volts, and coming across here we're going to have about 1.05 milliamps for IPQ. Next, let's determine our AC equivalent resistances. So starting with R prime L, that's equal to RP in this case, which is 100 k ohms, and R prime P, which is our small signal AC plate resistance, that's equal to R prime L in parallel with little rp. So we've got 100k in parallel with 60k, and that comes out to be about 38 k ohms. All right, our AC cathode resistance is the same as the DC cathode resistance, that is R prime K equals RK, and that's 1 k ohm. Now let's go ahead and find the voltage gain for V2A. That's going to be AV equals negative GM times R prime P over 1 plus GM times R prime K. So we've got negative 1.6 millimos times 38 k ohms divided by 1 plus 1.6 millimos times 1 k ohm. And our numerator works out to be about negative 61 divided by 2.6 for an overall voltage gain of about negative 23.5. Now, next on our list of things to do is to plot the AC load line, but in this case, because R prime L equals RP, we're going to have an AC load line that's identical to our DC load line. So we don't even really need to plot it. It's already here. So let me just make a note. AC load line equals DC load line. And that's because the effective load resistance is the same as the plate resistance, and the same with our cathode resistance in the AC and DC equivalents as well, although it has a relatively minor effect here. Next, we're going to analyze the second half of this amplifier, but before we do that, let's just go on over and look at the condensed version of what we've covered so far, and here it is. I'll pause here for a second or two so that you can do a screen capture or look at this a little bit more closely. And now let's go on and take a look at the second half of this circuit. I've included the plate current and plate voltage for the section we just completed. And looking at the second half of this circuit, we see that the DC load line is going to be identical to the DC load line for the first half. That's because the total resistance from plate to ground is almost identical for both stages. We've got this extra 1K here, but that's insignificant. So we're going to have the same DC load line over here, and that gives us VPK cutoff equals VPP equals 260 volts. Again, IP sat is VPP over RK, 260 volts divided by 100K is again 2.6 milliamps. And let's draw our DC load line, 2.6 milliamps to 260 volts. And there we go. Okay, I'm going to record these values at the endpoints, 2.6 milliamps and 260 volts. And now let's get started on our bias line. This time things are going to be a little bit different. We are going to do this little chart that has VGK and the resulting I sub P, but this time the equation for I sub P is going to be different. That's because our grid is not sitting at 0 volts anymore. This time it's sitting at the plate voltage of V2A, that's 155 volts. So we have to modify our equation for I sub P, and what we get is I sub P equals V sub P A, that is the plate voltage for V2A, minus VGK, the grid to cathode voltage for the second triode, divided by R sub K. All right, and again, we can start by picking VGK equals 0 volts. All right, we just plug that in here, so we have 155 minus 0 divided by 100K, and that gives us 1.55 milliamps. So with 0 VGK, we have 1.55 milliamps plate current flowing down through the right side. And that should make sense. If we had 155 volts here, 0 volts dropped from grid to cathode, that means we have 155 volts here, and I equals V over R, 155 divided by 100K is 1.55 mils. All right, next we're going to pick a convenient VGK value over here from these curves. And somewhat arbitrarily, I'm going to use the negative 3 volt curve over here. So VGK is negative 3.0 volts. And the resulting I sub P is going to be 155 volts minus negative 3 or plus 3 volts divided by 100K. So that's 158 volts over 100K which is 1.58 milliamps. So here we have 1.58 milliamps. So now let's locate these two endpoints. I'll switch to green here, and 0 volts, 1.55 milliamps is right here. Negative 3 volt curve at 1.58 milliamps, that would be right here. And now we'll connect these two up with a straight line, and this is our biasing line. Now, it might seem kind of weird that our bias line is so flat, but in this case, remember, we're dealing with a really large cathode resistor, 100 k ohms. Normally on the graphs that we've done like this, we're dealing with maybe a couple thousand ohms down here, and that's going to give us a much steeper line than this. So remember, the bigger RK is, the flatter this line is going to be. All right, so let's switch colors here to purple for some contrast, and let's draw in our Q point. And it looks like our VPK value is about 105 volts, and our IPQ value looks like maybe about 1.6 milliamps. Okay, let's clean up the workspace a little bit here, and then we'll do our AC analysis. So there we go, and that looks pretty good. So let's start out by switching back to blue, and we'll find our R prime K value, which is equal to RK in parallel with RL, and RL is the tone stack, which is going to have a variable impedance depending on the frequency we're operating at and how our potentiometers are set, but on average it's going to look something like around 50,000 ohms. So we'll go with that, and we've got 100K in parallel with 50K, which gives us an equivalent resistance of about 33.3 k ohms. Now we can determine the voltage gain of V2B, and since this is a cathode follower, the gain should be pretty close to 1. The actual gain equation is A sub V equals GM times R prime K divided by 1 plus GM times R prime K. And if you want a review of where this equation comes from, we've derived it back in video 66, and you can see where that comes from. But in this case, let's jump down here. We've got AV equals GM 1.6 millimos times RK 33.3 K divided by 1 plus 1.6 millimos times 33.3 K, and that gives us about 53.3 divided by 54.3, which is voltage gain of about 0.91. So it is pretty close to 1, and we could just approximate it as 1, but there you go. All right, I took the last nanosecond to erase the space down here, and let's write in our gain here, 0.91. And now we'll work on our AC load line limits. And we know that in the most general case, IP sat is equal to IPQ plus VPKQ divided by R prime L plus R prime K. So we don't have a traditional load resistor up here like the common cathode version would. So this term is equal to 0. And so we're just working with R prime K in our denominator. And we've got 1.6 milliamps plus 105 volts divided by 33.3 k ohms. So we've got 1.6 milliamps plus, this works out to be about 3.2 milliamps, which gives us an IP sat of 4.8 milliamps. Now that's off of our graph here, and if we wanted to, we could extend this up and add on to this scale, but let's not worry about that for now. Let's just go ahead and find VPK cutoff, and again in the most general form, VPK cutoff is VPK Q plus IPQ times R prime L, that would be our load resistance for the common cathode version, plus R prime K. But again, we only have R prime K, so R prime L is equal to 0, which gives us 105 volts plus 1.6 milliamps times 33.3 K. That's 105 volts plus, this works out to be about 53 volts for a total VPK cutoff of 158 volts. All right, so let's switch to red and we'll plot, well, we can't plot this end, but we'll go from VPK cutoff 158 up through the Q point, and that's going to look about like this. And if we extended this axis up, it would probably intersect really close to 4.8 milliamps. But there is our AC load line. Now, I guess I should mention that if you're just coming into this video cold without having seen any of my previous videos, you might be wondering where the heck all these equations and formulas are coming from. And if that's the case, you might want to go back to, say, video 62, where I go through the original analysis of triodes using AC and DC load lines and so on. But it's all back there. If you don't understand what's going on, I do cover all the basics that I've used in all of these videos. You just have to go back and review those. But for now, that almost completes this analysis. What we're going to do next is come on over and look at a nice version of this as usual. And here we are, okay, with everything summarized, and I'll give you a second to study this and then we'll move on. Now, if you've been doing the calculations along with me here, you'll note that I did make a slight mistake here. I had a typo or read my calculator wrong, whatever. In any case, this voltage gain should not be 0.91. 53.3 over 54.3 is 0.98. So let me make that correction here. This should be 0.98. And hopefully you guys all caught that anyway, but there's the corrected version. And I've got one more slight thing to fix here. This VPKQ should be 105 volts, not 155. So let me fix that. There we go. And wow, this was a tough one. I'm still not over being sick all last week, I think. So, hopefully that's all I screwed up in this video. But there we go. Everything should be caught up. And now let's go on over and look at these results on the schematic. Let's start by looking at V2A. We calculated 1.05 milliamps for plate current and VPK of 155 volts, and that'll be approximately the same as its plate voltage as well. We've only got about 1 volt dropped across R16 here. Now this is directly driving V2B, and we calculated 1.6 milliamps plate current here, which gave us a VPK of 105 volts. Remember, it's plate to cathode that we calculated, not plate voltage. That's 260. We're going to have about 105 dropped across the tube itself. And if we have 1.6 milliamps plate current, that should give us 160 volts down here at the cathode. And notice we do have a bit of a discrepancy here between the grid and the cathode. 155 volts at the grid, 160 at the cathode. We know it's not going to be that big of a difference. We really only have about a 1 volt difference from cathode to grid. But this is all based on graphical analysis, so all things considered, it's actually pretty darn good. And now, normally I would construct the circuit and make all these measurements, but I just don't have the energy to do that this time. But I did do a piece-by-piece simulation of this third stage, so we'll look at that next. All right, here's our schematic editor with the circuit constructed. I do have a 260 volt power supply connected to this thing, but let's go ahead and look at our currents first. And for TU1, which would be V2A, we have a plate current of 994 microamps. So it's slightly less than the 1.05 milliamps we calculated. Pretty good. For V2B, that's this second triode, we have 1.6 milliamps. It's right on the money with what we calculated, so just about perfect. And let's take a look at our voltages. We've got 160 volts here at the first plate. We calculated 155. But remember, it's going to be a little bit different. We have 160.6 volts here on the cathode resistor for the second half. We have 160 calculated here. Very good agreement. And everything looks really good. So I would expect that this would come out pretty much right on the money if I constructed it as well. And now what I would like you guys to do is to check these voltages and currents against the data that's published online and see how close we are. I have a pretty good suspicion that we're very close. I'm not going to search for those results right now, but that's something you might be interested in trying. And that's all I've got for you today. I will possibly continue with some more analysis of amplifiers out there in the world, and if there's any amplifier that you might want me to take a look at, let me know. I can't promise that I can get to it, but I'll at least consider it. And that's it for today. I'll see you guys next time around.